Okay, so in this tutorial, I'm going to be going over k-means clustering, which is a data mining technique, and the goal is to cluster the data based off of similarity. So in this first code cell, we're just going to create some made-up data that we're just going to use as an example, and we're going to implement this algorithm, the k-means algorithm, by hand. Most of the time, though, you're going to actually already have access to the k-means algorithm or other machine learning algorithms or data mining algorithms through packages that you can import through Python or install through other programming languages and use them there. But in this case, it's just going to go more in depth to give you a better understanding of what it's like to implement the algorithm, and it helps you understand how the algorithm works step by step. So this is a list of lists. Each element within our list is a data point. We have the x-axis right here and the y-axis here, x-axis, y-axis, x-axis, y-axis. So it's going to go all the way down. And if you run this code, you can press Control Enter, and we'll have data points right here plotted. And you can already see that these data appear to be clustering right here. Now, when we're doing k-means clustering, we want to be able to cluster our groups, cluster the data into groups. At this point, I'm purposely choosing just x-axis and y-axis, just only two-dimensional data points, but it could be, you could have three dimensions, 4, 5, 6, x amount, and it gets a little bit harder. So k-means clustering can help us cluster the data together when there's more data points instead of looking at it visually. So at this point, we're going to start using the k-means clustering algorithm from step 1 all the way to step 4. So first we need to actually initialize our k-centroids or number of partitions. So in this case, visually we can see that there's 3 clusters. So in this case we can just say, let's start off with k equals 3. And then we're going to initialize the 3 centroids. So we're just going to pick 3 random points within our data set and call those our centroids. After we assign our centroids, we're going to calculate the distance from a centroid to each data point. So if we run this code right here, we're going to initialize the k centroids, and I'm going to color them yellow, red, and green. So Control Enter, and then we have our initial centroids. So I just choose, so this code right here is just going to choose 3 random points within our data set. Okay, k equals 3. We're just going to randomly sample, and we're going to choose 3 of those data points, and then I'm going to plot them here and color them a different color so we can see them. So here's one centroid, second centroid, here's a third centroid. Next, we're going to take this centroid right here, and we're going to calculate the distance from this centroid to this dot, this centroid to this dot, to this dot, to this point, to this point, and then we're going to do every single point, and we're going to assign the closest point to a centroid. So obviously you can see visually that this point right here is closest to this initial k than to this initial k. And notice how this initial k is closer to this point than this point is, right? So we're going to calculate the distances from each point for each initial k. So this initial k will calculate distances, this point to this point, this point to this point, and then the same thing for this one, this point, calculate this for this point, and this point, and then assign the points closest to their initial k. So we can do that here. And to actually go and to figure out what distances we're going to use, there's different methods you can use to calculate the distance from, or the similarity of the centroids to those points. So we see how we're calculating an initial k here to this point, here to here. We're going to use for this example, we're just using the Euclidean distance. We're going to use this formula here, and then we're going to assign them. So here we can run Control Enter, and then the points that are closest to each other, we're going to color them. Here we have red, 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 yellow. So notice how we're coloring them based off of how close they were to the initial centroids. Then we need to recalculate the centroid positions. So notice how from this point we got pretty lucky right here. We just chose random points, but I've run this code again. The points aren't going to be in the same position, right? So this point might be colored green, and same with this point. This point might be colored green as well because it's closer. This one might be alone. It might be the only yellow one. This point will all be red. So we can test that and see if that's actually right or not. And see what we get here. So exactly what I said. We get some green right here. We have some one yellow, and we have all these being red because here we have the initial K closest to all these. We have green being closest to these points, and then yellow is going to be alone. And then you can see the coloring there. Then we need to recalculate the centroid positions. So we're going to take this red group and calculate the mean, and then plot that point. Take this green group, calculate the mean, plot that point as well, and calculate this yellow point right here, and calculate the mean, which is just going to be itself. So this is what that code does right here. So we can Control Enter, and here it is. So we have the green, we have the red right here. So this is the mean right here of the red group. This is the mean for the yellow group, and like I said earlier, this is going to be the mean for the yellow group, or for the yellow point. So that's the third point, is just recalculating the centroid positions. And then you just go back to step 1 or step 2, and you're going to calculate the distances and then assign them to their new group. So you're going to iterate this, and you're going to keep iterating it, iterating through until the centroid points do not move anymore. So putting this together, we can start iterating to steps 2 and 3. Assign the centroids, calculate the distances, assign the points closest to the centroids, and then recalculate the centroids. And then we're going to have to reassign the positions. So we're going to have to run this program right here, or run this code right here. And this is going to do this iteratively. I'm going to use a while loop to keep running, to keep doing this iteration until the assignments don't change anymore. So we just click run right here. And then we get the output. So here's the means. So we got 3 means because we're starting off with 3 centroids. Or since we want K equal to be 3, so 3 clusters. And then here is the assignment 1, and then here's the new assignment. So this is just showing that the assignments are the same. We kept iterating until they were the same. They're not changing anymore, so leave the loop. We're done. And let's plot and see what happens here. So it looks like we got a pretty good result. We have the clusters appearing just the way that it looks like it should be clustering, right? Because when we first did the clustering at the top, or when we first just plotted it to see what our data looks like, it obviously looks like they cluster into 3 separate groups. And then using the k-means clustering algorithm that we have right here, it all clustered together pretty well, okay? And then to make the code reusable, I turned it into a function. So then we can take any type of data input, any type of list of lists with numbers in them, and then we can take k equals 4, k equals 3, k equals 2, and then assign them a different, or create 3 clusters, 2 clusters. You just give me a k, give me some data, and I can create however amount of data inputs you have. So just say you have 3 data inputs, or let's say 11 data inputs, you give me k equals 3, I'll create I'll cluster them into 3 groups. If you give me k equals 6, I'll cluster them into 6 groups, and so forth. Okay, so we can run this here, run this function. It's not going to do anything, but when we run here, we're actually going to be using the function to cluster our data points. Enter, okay, control enter, and we can run this as well and see what we get. So it clustered together well, similar result. And the next, you might be asking, well, what if we have more than 11 data points like we have here? And how do you know what k to actually choose? We just chose 3 because it looked like it should be 3. But sometimes you might not be as clear and you might not know how many clusters there should be. So at this point, we can use the elbow method, which is going to take the sum of square errors for each possible k, and we're going to plot on the y-axis the sum of square error, and then on the x-axis is going to be the number of k. So here you can see that the results are somewhat different, but you can actually keep running this, keep running it, and then eventually you'll get a k, then you'll get an elbow right here. Where the elbow forms, that's the k that you should, that's like the optimal k that you should use. So k equals 3. Now this also goes into just how it is when you're using the k-means algorithm. Notice how we're randomly choosing k. We're randomly choosing our initial centroids. So it's possible that our graphs won't look the same. It won't cluster the same every single time. So if we run this and we run this, we keep running this, we might get some weird clustering like this green one here, and this yellows, and this red. It's not clustering the same every single time. We're not getting the same results every time. That's just due the fact that we are randomly choosing those centroids. See? But there is another algorithm that we can implement here for the initialization process. So this is naive Shards initialization algorithm, and it's going to change the way that we initially choose the 3 initial centroids. Instead of doing it randomly, we're going to first start with each row and sum the columns value and append the total to the row as a new column. And then we're going to sort based off the new sum column by ascending order. We're going to split the data horizontally into k equal size pieces or shards. And then for each shard sum column values, we're going to calculate the mean and add each mean to a separate set. Then we're going to calculate each centroid, or add each centroid. So step 4 is actually going to be calculating that centroid for the shard. And then step 5, we're going to add each centroid, calculate each shard in step 4. So in step 4, we calculated 1 shard. So in this point, we have 3 data points, or we have 11 data points. And for those 11 data points, we're going to split them, or try to split them in halves. So after you actually compute the sums and you add the sum to the list, you're going to split it in half. Okay, and well, 3 equals shards right here, 3 equals shard pieces. So it's going to be 3, 3, and 5, because we have 11 here. So 1, 2, 3, 1, 2, 3, and then 1, 2, 3, 4, 5. Okay, so there's going to be three equal size shards, at least try to get equal size shards. And then at the end, then we're going to, for each shard that we create, we're going to sum the column values, calculate the mean for each one, for each column value, and that's going to be a point in our centroid. Then we're going to add each centroid to a separate list until we have the k centroids. And then we can use those centroids as our k-means initialization step. So this code right here that I have right here for you is implementing the naive sharding algorithm. So you can click run. Here's our k centroids. We have 3 centroids right here. And then finally, this is the k-means algorithm again, but this time we have an option to implement our initialization algorithm that we just implemented from above. And this time we will get the same results every time. So control enter, control enter, one more time. So the result's going to be the same every time. So this is k-means clustering.